We're going to examine what's called the uniform distribution. But before we turn to that, it's important to remember that uh, continuous probability distributions can take on all types of different shapes and sizes. Well, I don't know if sizes make sense, but they're going to take all different types of shapes, right? That can be a distribution. A distribution could be, something like that. We can have one that we'll turn to later. It can be a nice, smooth, normal distribution, and one other one that it can take and is something where it's a flat line straight across, and that's the uniform distribution. So that's what we're going to turn to here. But I do think it's important to remember that this is just one of a myriad type of different distributions or shapes of distributions. Now, this is a rather specific distribution. Okay, it doesn't occur often in the real world, and we're being very particular that it has a very straight, even distribution. Now, the reason we're spending some time on this is because it's a great way to dig into what we're trying to do mathematically and trying to do as far as describing a distribution. Remember in chapter 6, we did this with the discrete distributions. Here we're trying to do the same thing. We're trying to summarize the distribution with things like the mean and the standard deviation. And we're trying to depict it graphically. And then lastly, we're trying to be able to describe certain outcomes. So in our continuous world, that's going to be a range of outcomes. In the discrete world, we may have talked about a specific value, but here we're going to talk about, what are the chances between certain values. So that's what we're going to do, and we're going to use the uniform distribution to be able to focus on our goals and not get too bogged down in the math, because the math, it turns out, is quite simple here, because largely we're going to be working with rectangles. So I just want to put that out there at the start, is that this is not the most widely you don't come across this as often. The assumptions to be a uniform distribution are pretty strong, but it's helpful for our examination of this. So your book walks through an example, and we did this in lecture of kind of bus arrival times. Let's try a slightly different example, but the basis here is going to be the same. So let's say I have I have a fancy I have a Ken Griffey, maybe not his Ken Griffey Jr. Maybe not his rookie card, but it's a good card, and I know it has value somewhere between, let's say it's somewhere between $7 and $13. Okay, that's the value of this card. You could, if you're not this is a Griffey Jr. Maybe you want to swap that out and say it's some Pokemon card. Anyway, you have a card. The value is between $7 and $13. That's all you know. And in fact, you don't know any. There's no reason for you to think that it's more likely to be 7 or 13 or 12 or 11.93. You just know it's somewhere in that range. And so the distribution of possible values is uniform. It's just simply spread out across this range of values. So we may want to dig deeper into this and describe maybe what the mean is. Another way to say, what is the expected value of this? So we're gonna calculate the mean, the standard deviation of this distribution, and we've already kind of depicted it here, but we want to be able to measure the height of this, and then also find, maybe we're curious, what's the chance that it's greater than a certain value or between two values. So let's walk through this. The mean, and of course, with such a simple example, we could probably logic our way to knowing the middle of this range here. But the mean in general is going to be b minus a. Now, what is b and a? So we label, in a uniform distribution, we simply label b and a as the two endpoints of our distribution. So the mean is simply b minus a divided by 2, right? We're just finding the midpoint of this line. So for us, that becomes 13 minus 7 divided by 2, which is 20 divided by 2, which is 10, right? So again, we could have gotten there with just kind of examining the situation, but this is more flexible. If you have, if it was 7.06 to 13.23, we could still find the mean with this method. And so one way we would be able to describe this is that our expected value of this card is $10. Now, if we want to talk about the spread of this distribution, we would turn to the standard deviation. I guess we're familiar. I can just keep it as sigma, and that has a very particular equation as well, and that is b minus a squared. Okay, so the square root of b minus a squared, right, and then divided by 12. Okay, it's kind of a formula you just have to rely upon at this point. As I mentioned in class, if you take further courses, maybe an econometrics course here, we can dig deeper into that. If you are curious, we can chat about it at office hours. But if we plug in 13 minus 7 here, square that, still divided by 12, get that square root all the way over. We can see, let's just do that down here. That's going to be 6, so it's going to be 36 over 12 square root, and that's going to be the square root of 3, which is about let's just call it 1.73. So we have a standard deviation of 1.73. Okay, and that would give a person, in a uniform distribution, we can usually just talk about the two endpoints. But in general, with continuous distributions, we do want to be able to describe it with the mean and the standard deviation. Again, in this particular case, the standard deviation is less helpful because we can just depict the whole thing with the endpoints. Okay, so to go a little further, if we want to start examining what are possible ranges of outcomes and what's the likelihood of falling within a certain range, what we're really after here is to find the area of certain ranges under the curve, right? So if for instance we want to find the likelihood of that it's between 8 and 950, we would need to find this area, remembering that the whole area has to be equal to 100%. Okay, so this kind of smaller sliver here between 8 and 9.5 is some share of the greater 100% probability, right? So all of the outcomes are contained between 7 and 13, and they're all equally likely in this uniform distribution. So that whole thing equals 100%. And the middle part here, or the part shaded in red, is the part that we may be interested in. Let's say that we're curious the percent likelihood that it's between 8 and 9.5. So we simply need to find the area under that between the 8 and the 9.5. To do that, we're going to need to know the height of this line, right? So we're simply going to want to do height times the base. And to do that, we need to figure out the height. So how do we do that with a uniform distribution? Let me just switch colors one more time. To find the height, we do this equation. So 1 over b minus a is going to be the height. And that gives, in our case, 1 over 13 minus 7, or 1/6. Whoops. Okay, so in our case here, the height is 1/6. And we could probably, again, figure that out without the formula in that, this is a distance of 6 units. And so if it's all going to multiply, if the area is going to be 1, right, we need the area to be 1 or 100%, 1.00. Then what we really want for the area is we need it to be 6 times 1/6. That's supposed to be a 6 down there, equals 1. Okay, that might be another way to kind of conceptualize what's happening here, is that we need all of the area in this green rectangle to be 100% or 1.0. And so if the base is 6, then it must be that the height is 1 over 6. Okay, so that's really what the height formula is doing for us, is just making that conversion. So to again focus in, what if we want the height times the base of the red? Well, we know the height now. And so we know this is 1/6 times, what's the base? Well, it's 9.5 minus 8. So it's 1.5. So we get, what is that going to be? 1.5. We can put, so 3 equals 1/6 and 3/2. So we have 3/12. Is that 1/4? So we get a likelihood here. So 0.25. Okay, or 1. Well, gotta move the screen. 0.25. So there's a 25% chance that it falls within that range, right? Again, we probably could have logicked our way there as 1.5, and the whole distance is 6, so we're 1/4 of the area. So that's the process, though, of finding the area under this range in the curve, right? So we were curious about it falling between 8 and 9.5, and we know that that's a 25% chance. And this is the general process that we're going to do with any continuous distribution. We're curious about an area, or we're curious about the likelihood between a range, and to figure that out, we're going to calculate the area. Okay, it just so happens that this is the simplest math. It gets more complicated when we have more complicated distributions. Another thing you might be interested in, and let's just take a minute to think about this. So what if we thought about 10? What if you were curious about the likelihood that it's greater than 10? We could go through the same process. Okay, we know the height is 1/6. So what's the probability of greater than or equal to 10? We know it's 1/6, the height, times the base, which is 3, or 1/2. Okay, so there's a 50% chance. Now, the reason I bring that up is this is a symmetrical distribution, right? It's even on both sides of the mean. And so one thing we can rely upon for symmetrical distributions is that each side of the mean is 50% of the distribution. That's going to be helpful when we turn and look at things like the normal distribution. So I just wanted to mention it here and kind of get it in the back of our heads, that we can use kind of simple logic to help us out calculating certain percentages as well.